Okay, good afternoon, everybody. My name is Luis Salgado. I'm professor at Universidad Politécnica de Madrid, particularly in the image processing group. And I will be chairing today this afternoon session titled Cooperative System, a Vehicle Highway Systems. We have minor changes, not so minor. The second paper won't be presented. We have just received a notice that the speaker couldn't make it because some visa problems. So what we will do is to give a bit more time for the speakers. And up to now, the fourth talk, no one is shown up for it. So let's hope that along the session, the fourth speaker will come. Otherwise, we will end before and we will start with the coffee break earlier. Okay, so let's go for the first speaker this afternoon. It's Bernat Gogny-Ros, and he's going to present the paper Reducing Congestion at Uphill Freeway Sections by Means of a Gradient Compensation System.
Good afternoon. My name is Bernat Gogny-Ros. I'm a PhD candidate at TU Delft in the Netherlands. I'm going to present a paper that I wrote with three other members of my department, Victor Knoop, Bart van Arem, and Serge Hogendorn. And the paper is called Reducing Congestion at Uphill Freeway Sections by Means of a Gradient Compensation System. This is a part of a research project that is sponsored by Toyota Motor Europe. Congestion has creates a lot of problems for modern cities because it has some important negative effects on society, including travel time delay, travel time unpredictability, traffic accidents, and others. And in hilly countries, congestion usually occurs in uphill freeway sections. In particular, this is a major problem in Japan, in which the number of traffic jams that occur in this kind of sections in which gradient changes is more than 20%. So it is a big problem in this country. Here I show an example of a typical freeway section in which congestion occurs. We have, in this kind of sections, we have uphill sections longer than 1 kilometer, more or less, gradients between 1% and 6%. And when congestion occurs, the head of the queue stays more or less within the first 500 and 1,000 meters. Our contribution to solve or to reduce congestion at uphill freeway sections is the concept of a system that we call a gradient compensation system that assists the driver in performing the acceleration task while the vehicle is on an uphill section. We think that this can have positive effects on traffic flow efficiency, and that's what we test in this paper. And actually, I will show you later that this system could help reduce congestion at uphill freeway sections. Why does congestion occur in uphill freeway sections? Sorry. Well, we can see it in this graph. One of the main reasons is in this graph we can see location in the road in the x-axis, and in the y-axis we have the vehicle speed. This black line is the vertical profile of the road. The uphill section starts around here, and in this particular location, the speed of the vehicle starts to decrease because of the increase in resistance force. And more or less, it's according to literature, the speed drop of the vehicle reaches more or less 10% of the initial speed. And then the drivers are able to reaccelerate again. What happens is that this speed drop generates a traffic flow disturbance, and in particular conditions of high traffic demand, and depending on the magnitude of this speed drop, this can destabilize traffic flow. This means, as we can see in these pictures, we have 4 cars going up an uphill section. When traffic gets unstable, this means that the speed drop of the 4th vehicle, this curve here, shows a stronger deceleration than the deceleration of the first car. So the deceleration gets stronger and stronger as the traffic flow perturbation propagates backwards. This can lead to a traffic breakdown and the formation of congestion. How does the system that we propose work? Well, it's first of all, I would say it's a concept system. So it's basically, at this stage, a concept. The gradient compensation system monitors continuously the freeway gradient by means of a digital map. It also monitors the position of the throttle and brake pedals, the gear selected, and the vehicle speed. Then the system will activate when three conditions are met. The first of all is that the vehicle, according to the digital map, is on an uphill section. The second one is that the driver wishes to keep a constant speed, and this is monitored by means of the monitoring the throttle and pedal, the throttle pedal position, and also the gear. And then the gradient compensation system will activate only when the speed of the vehicle has decreased by 5% in the uphill section. What happens when the system activates is that the system will assist the driver in performing the acceleration task by changing and dynamically adapting the relationship between throttle position and the engine power. As a result, the vehicle will be able to accelerate again and reach the initial speed. The only thing that the driver needs to do is to keep a constant throttle position during the whole process. So, what is the effect of this system on the speed of the vehicle? Well, we can see it in this graph, where we can see the evolution of the vehicle speed over time for a vehicle that is not equipped with a gradient compensation system, that's the red line, and for a vehicle that is equipped with a gradient compensation system, that's the blue line. As we can see in this graph, because, at this point in time, the vehicle reaches the uphill section and the speed starts to decrease. But because the speed drop perception threshold of the system is lower, 5%, than that of a human driver, according to literature, around 10%, what we see is that the magnitude of the speed drop of the vehicle is decreased. We can see it here. The vehicle equipped with the GCS is able to re-accelerate to the initial speed faster than the human driver. And this has important consequences for traffic flow. The research question that we tried to address in our paper is whether traffic flow efficiency at uphill sections can be improved by equipping vehicles with this gradient compensation system. In order to evaluate this, we performed a traffic simulation study. And now I'm going to explain a little bit more in detail the characteristics of this traffic simulation study. First of all, we modeled a very simple network. This network consists of a freeway stretch 4 kilometers long, with a first section 2 kilometers long that is completely flat, and then a second section also 2 kilometers long, which is an uphill section with a gradient of 3 or 6% depending on the scenario. This freeway section has only one lane, so there are no overtaking opportunities possible. We also modeled a platoon of 300 vehicles, all of them of the same type for matters of simplicity, Toyota Yaris. And we equipped the first vehicle of this platoon with the gradient compensation system. We assume that the platoon leader has this system installed. In order to simulate traffic flow, we needed to model also longitudinal driving behavior, acceleration behavior. And we used two different models, one for the platoon leader and another one, a different one for the rest of the vehicles, the followers. The platoon leader is in free flow regime. There is no vehicle in front of him, so he just tries to keep its desired speed. And in order to model the acceleration behavior, we used a submicroscopic approach that takes into account submicroscopic variables like throttle position, gear, and also takes into account the gradient of the road to compute the vehicle dynamics on the road. For the followers, we took a more simplistic approach, and we used a microscopic car following model that takes into account only speed, relative speed, and headway to the vehicle in front. We modeled traffic flow in 12 different scenarios defined by different values of 3 variables: the speed drop perception threshold, the desired speed of the platoon leader, and the gradient of the uphill section. As I mentioned before, the speed drop perception threshold of the gradient compensation system is lower, 5%, than for a human driver, which we assume to be 10% or 15% depending on the scenario in our simulations. In order to evaluate the impact of the system on traffic flow efficiency, we used 2 different measures. The throughput, the first one is the throughput downstream of the bottleneck as a measure of capacity. And the second one would be the total travel time experienced by all drivers, all vehicles. I'm now going to explain the results. First of all, I would like to say that the results of all the scenarios without the gradient compensation system look very similar. And the results of all the scenarios with the gradient compensation system also look very similar to each other. So what I'm going to do is basically present the results for scenarios without and with the system. Here we can see speed contour plots. For those of you not familiar with traffic flow theory, basically what they show is the location on the road in the vertical axis and time on the horizontal axis. The uphill section starts, as I mentioned before, 2,000 meters. And the colors denote the speed. The darker colors mean lower speeds. As we can see in these 2 graphs, without the platoon leader being equipped with the gradient compensation system, congestion arises at the beginning of the uphill section and propagates backwards. Whereas if we equip the platoon leader with our system, congestion doesn't occur, which means that by reducing the magnitude of the speed drop at the uphill section, we are able to stabilize traffic flow. This has important consequences for the measures that I mentioned before, throughput and total travel time. First, throughput. We can see in this graph the change in throughput compared to a reference scenario with a flat, only a flat highway, so no uphill section. For the scenarios without the gradient compensation system, so with speed drops perception thresholds of 10 and 15%, and with the gradient compensation system. As you can see in this graph, if the platoon leader is not equipped with the gradient compensation system, there is a decrease of around 10%, depending on the scenario, around 10% in throughput downstream of the bottleneck. Whereas if we equip the vehicle, the first vehicle, with the gradient compensation system, what we see is that there is no decrease in throughput. With regard to the impact on total travel time, because without the gradient compensation system, there is a formation of congestion, we can see that total travel time experienced by all vehicles increases by around 20–25% in all the scenarios without the gradient compensation system. Whereas if we equip the first vehicle of the platoon with the gradient compensation system, we are able to actually prevent the formation of congestion, and therefore there is no increase in total travel time. So let me go now to the conclusions of our paper. We presented this concept of a system called gradient compensation system, which assists the driver in performing the acceleration task in uphill sections. We tried to answer the question, can traffic flow efficiency be improved by equipping the vehicles with a gradient compensation system? The approach we took to answer this question is a traffic simulation study with a sensitivity analysis. And the main findings of our study show that the gradient compensation system, at least equipping the first vehicle of a platoon with this system, could help reduce congestion and improve traffic flow efficiency. Therefore, this could be beneficial in terms of throughput and total travel times experienced by drivers. So that was the end of my presentation. Thank you for being here, and I am now open for your questions.
Okay, we have time for questions. Okay, the phone over here, please.
In my car, like in hundreds of millions of other cars, you have cruise control. And, in converting some functions that you have in the cruise control systems and an extra camera to keep the distance constant, you have the same thing, right? Okay.
I didn't understand your question then.
Yeah, the question is, a cruise control system serves a similar purpose, but you can convert it into some GCS by converting some minor functions, or reverting some minor functions of the cruise control system, and then you have you need an extra camera for that platoon leader. Mm-hmm. That's it, right?
You're asking me whether this is similar to a cruise control system?
Yeah, it's very similar.
Yeah, well, the idea is that our idea is to, we're assuming that this vehicle, of course, doesn't have any cruise control, or at least if it has it, the driver is not using it. And the difference with the main difference with the cruise control system is that this system doesn't take full control of the acceleration task. It only assists the driver in the uphill section, and so basically you don't have to tell your car when you're drive. So basically, when you are in the uphill section and you want to keep a constant speed, the car just helps you without the help of any cameras or any sensors in this case.
But you have to keep the distance to the platoon leader constant.
Mm-hmm.
Whatever means that is. That is not part of a cruise control system. Everything else that you can override it, that you have again for a cruise control system as well.
Again, I didn't understand your question then.
It's a comment, not a question.
Oh, okay. Well, in a way, I guess you're right, yeah.
Okay, more questions? Yes, behind you.
Okay, I have a question about your digital maps. So what is the advantage of taking digital maps with gradient information against or in comparison to using a sensor like you have in each smartphone, for example? So a digital map is a static information source, and streets can change. For example, you have a new bridge or something like this. And a sensor that dynamically records gradient information would cover these changes. Mm-hmm. So what is the advantage of taking digital map gradient information?
The quick question to your answer is that we really didn't decide yet in what kind of technology we are going to use or should be used to monitor gradient. Of course, you can use some kind of sensor also. Our idea was more to use some kind of more approach in which you don't need any sensor. That's the idea. But the whole point of the paper is not, as I mentioned during the presentation, this is more of a concept than actually. We really didn't go into depth on how this system should be designed. The idea is that the system should be able to continuously monitor gradient. And okay. We decided to do it to it by means of a digital map here, but it could be done also with a sensor. This, of course, doesn't...
Okay, thank you.
More questions? Over there, please. On that side.
Do you consider the scenario that the plantation is driving in the mixed traffic with other vehicles?
Yes, this is, of course, as I mentioned before, this is a very simplistic scenario, as you already guessed, in which there are many things that we didn't take into account. For example, a more complex network with overtaking possibilities with different lanes, different like heterogeneity of the composition of traffic flow, so different kinds of vehicles, different kinds of drivers, and also different kinds of different traffic conditions. This is work that we are developing right now, so improve the driving models to and the controller to make it effective in more complex conditions. And the idea of the paper was basically to prove the concept in a more simplistic way. But we are, as you said, we are now working in how to improve our system to make it work in more complex conditions.
More questions? I have a curiosity. You have assumed that only this system is on the first vehicle. How would it affect that all of them are equipped with the same thing?
Yes, I will show you this picture. Here, as you say, there is a platoon of 300 vehicles. This is also a very long platoon that actually we don't find in reality. So in reality, what we would find is more smaller platoons with gaps between them. If you had a percentage of cars of the traffic flow equipped with the system, we think this could even this could even stabilize traffic flow further, because then any possible shock waves, traffic flow perturbations that travel backwards could be also less traffic flow perturbations would be created by these vehicles which are after the first one. But the idea here, of course, was to have a platoon and then show whether stabilizing the traffic flow by this system could work, whether it works or not. Of course, as you said, in normal traffic, if this system was in the market, more vehicles would have it, and probably then the beneficial impacts of it, I guess, would be more. But we didn't look into it yet.
Another thing is you have chosen, maybe I'm wrong, but the pattern, the reacceleration pattern for the system and for the human being, you have used the same pattern or not?
It is the, you mean this one? Yeah.
Yeah, the pattern you have followed is the same one.
You mean this one?
Yeah.
Yeah, and in this case, we assume that when the driver perceives the speed drop, is able to accelerate in the same way as the system. So the system doesn't accelerate more stronger or less stronger. What it does is it reaccelerates faster at an earlier point in time.
Do you think this is real, more or less?
What exactly is real?
Yeah, this pattern, that is exactly the same. I mean, not exactly the same, but my guessing is that maybe the human being would accelerate more strongly, faster, typically than something that is mechanical and is perfectly adapted to the engine and things like this. So it's more abrupt. That's. This could be,
yeah. In this sense, however, I didn't present the results here, but the most important thing, the thing that had the strongest impact on traffic flow efficiency or traffic flow stability, sorry, was the speed drop magnitude. So how fast is the vehicle able to reaccelerate, to start reaccelerating actually?
So if the pattern is the same, this would be that the gain is that you are warned in advance, some seconds before, and then what you expect the human being is going to do. So it could be sort of a kind of bee that tells you, do it.
It could be, also, it could be.
And my last comment or question is, if this is the same pattern, have you measured the threshold in seconds, the gain that you need in time in order to overcome the traffic jam? I mean, this sure is possible to be guessed in such a condition, because it's with the vehicles with the same distance and all very static. You could also guess for the different speeds and different slopes what would be the gain in time that you require in order to avoid the traffic jam. Wouldn't it be possible?
I didn't get your question. Can you repeat it?
If it's a matter of gaining some time, advancing some time the acceleration. So have you measured any threshold, for example, for 95 kilometers and a speed of and a slope of these degrees? You need to gain 5 seconds, 6 seconds, 3 seconds, and then changing these variables, I'm pretty sure that you can try to advance what would be the required gain in order to get exactly the same results.
Okay, what we the idea behind this, maybe I should explain something. The idea behind this this pattern of reacceleration here is that the driver, because we looked at the literature, according to several studies, what seems to be the cause of the decrease in speed is that at this point the driver does not perceive that there is a change in gradient. So the vehicle will start decelerating, but he doesn't notice it because it's a short speed drop. It's not like going from 100 to 70. It's like 100 to 95 for maybe at the beginning. So he only notices the speed drop once it has gone below a certain threshold. And what we got from literature is speed drop perception thresholds for human beings of around 10%. If you could, this is average for all kind of gradients in between 1 or 6%, more or less average. If you could tell the driver to accelerate faster, to accelerate more in the uphill section, in the flat section, so that it could have more power once it reaches the beginning of the uphill section, this could be a solution also.
Okay, so thanks, the speaker.
Welcome to my presentation. Well, broadly speaking, I talk about traffic jam avoidance by the means of a distributed swarm intelligence approach, and we call our approach bee-inspired jam avoidance, or for short, BJammer. So here's my outline. First of all, I'd like to motivate the problems and our goals. Afterwards, I'll touch upon the necessary backgrounds, and then I'll present our distributed traffic management approach. So to start with, I think we can state that traffic congestions are nowadays one of the main causes for traffic delays. And the reason why traffic congestions or traffic flow in general is so hard to optimize is that traffic is really highly dynamic and highly unpredictable. However, traditional approaches as well as many research projects do involve at least one centralized processing step. And as a consequence, these approaches do not scale up very well to large regions as necessary in reality. So, for example, some commercially available systems operate in the range of a few minutes and only on selected roads. And we argue that this is not enough, and we argue in addition that traffic congestions are not really manageable by such centralized system, at least for large areas. So what we want to do, in contrast to many other projects, is that we want to give individual routing recommendations for each vehicle before each intersection in due time, based on up-to-date traffic information. So we do not want to rely on self-fulfilling prophecies like forecasting, for example. And of course we go for seamlessly scalability to very large regions. So that means that the information dissemination in our system must happen very fast in due time. So what is needed to meet these constraints is a completely self-adaptive and completely distributed management. So here is a brief sketch of our approach. So if you want, we use some kind of a divide and conquer strategy. We have local navigators issuing routing recommendations in a spatially limited area. And you can see an example of a navigator here. It can be deployed as in roadside hardware or as some kind of a cloud application, for example. And since we are in a decentralized system, we cannot rely on global information. That means that maybe our routing recommendations will not be perfect or optimal in some sense, but we want at least to ensure that the underlying information of our routing recommendations are accurate with respect to the general target direction, and we want also to ensure that the closer the target is, the more accurate the information becomes. And to cope with the highly dynamic traffic phenomena, we want to offer update frequencies of 1 second. So to implement these features, we're going to exploit swarm intelligence, especially as found in the foraging behavior of honeybees. So here's what happens in nature. Most of the time, so-called scouts try to discover food sources in the direct vicinity of the hive. But from time to time, the hive emits so-called long-distance bees. And these long-distance bees fly up to 12 kilometers, and by chance, such a scout may discover a new food source in this remote location. We call it a foraging region, which is the whole area in contrast to the foraging zone, where precise information is given, and here's only rough coverage given. So what happens if such a scout finds a food source is that it flies back and performs the well-known waggle dance, sharing information about sharing information about the rough direction, the distance, the quality, and the smell. And what may happen at the dance floor in the beehive is that unemployed foragers may extract this information and stochastically decide to go for these recently discovered food sources. So what happens is that the forager flies in the rough direction for the given distance, and in the destination area, the forager uses its sense of smell to pinpoint the actual location. So in total, there is no centralized assignment or something like this. Everything happens in a distributed fashion. So here's a mapping of concepts. We mapped food sources to destinations, as we'll see, scouts to bee agents, foragers to vehicles, and we identified the dance floor as the routing table, and we associated a hive with each node in the network. So here's a network example. Let's imagine that the hive at node 4 emits a short distance bee. What happens in nature is that eventually the scout will discover the food source, but this is going to not happen in the algorithm. So the algorithm starts right now, after the scout has discovered a food source. What happens is that the bee returns to the hive as in nature and performs the waggle dance that is updating the routing table. But it would be some kind of wastage if the bee does not update all the tables on its path back to the origin hive. So in this case, also node 5 receives an update. But not only these two nodes are capable of reaching this destination with short distance bees, but all nodes in the vicinity, in the local vicinity of the destination. So if we define this local vicinity, the foraging zone, by a given hop limit, for example, 2 in this little toy example, then all these nodes in the red box are capable of reaching the destination 7. In turn, this means that all these nodes must receive a returning bee, and this is best achieved, obviously, with some kind of flooding mechanism as indicated here by the animation. So it holds true that after one generation of bees, all nodes in the foraging zone of node 7 know how to reach node 7 best. And it emerges a self-adaptive and distributed path, and as we'll see, delay exploration approach. The next basic concept is the concept of foraging regions. In the most basic version, foraging regions are a predefined and static, strongly connected subset of nodes as indicated by the blue box. The basic idea is that a foraging region is represented by a so-called representative node. Only representative nodes are allowed to launch long-distance bees. So what happens is that the behavior of the scouts are exactly the same as the short-distance bees, as long as they stay in the foraging zone of the emitting node. But these bees are allowed to leave the foraging zone, and the basic idea is that if a vehicle is somewhere here, it is routed in the rough direction. So if the destination of a vehicle at node 1, for example, is node 9, the vehicle is routed in the direction of the representative node 8, and until it gets into the foraging zone of node 9, which is in this simple example the same as of node 8. So, sorry, yes, the basic idea. So, not only one node emits bees, but all nodes in the network. So some kind of flooding emerges, and here we can see the first step, but it repeats all the time. So now let's have a look at the concept of the routing decisions. Once again, imagine node 5 emits bees. I focused just on these two bees. I omitted the other bees. What happens is that the bees request the delays from the local navigator and traverse through the graph, so that node 10 learns that there are two paths to the destination 5, one path via 6 and one path via node 7 as next node. And the node also knows that this path is the faster one. So if a vehicle with destination 5 proceeds to node 10, the local navigator is able to stochastically choose the next hop only depending on these local information. So, for example, in this simple case, this edge is taken, and this process repeats until the destination is reached. And I'd like to stress that really only local information is used, not some kind of global information like in a static and global optimization process. So in total, it is a hop-to-hop routing approach. So it's time to put everything together. Here we have the navigator responsible for a limited area, and these navigators are responsible for continuous vehicle communication, for collecting, for example, floating car data or something else, to have at least a rough knowledge of the edge usages and loads and remaining capacities, and for sending and receiving the bees and updating the tables. But in reality, we not only have one area, but a lot of, in this simple example, 3, B, C, and D. And to each of these areas, a navigator is associated, omitted in these two callouts. And what happens is that short bees are used to disseminate local routing information and delay information, especially using these short distance bees in the specific areas. But typically, vehicles don't want to stop in their current area. Most of the time, they want to travel farther distances, and so we need some kind of inter-area routing. And for this case, we have a so-called net area. As you can see, on the net area, the inner nodes are omitted. Only the border nodes of the areas on the area layer are present on the net layer. And on the net layer, now, once again, short-distance bees, but also, as described, long-distance bees traverse the whole graph. And, well, that's what I've presented is at least the most basic version of BeeJammer. I skipped a lot of technical details, for example, aggregation of agents' information across layers, and so on. But it is still working, as we'll see on the next slide. So what we can see here is an OpenStreetMap from the eastern part of the German Ruhr district. About 1.5 million people live in this area. And the first step is to prune each node in the network that is not relevant to routing. For example, nodes that are used to giving shape to the edges, everything like this is removed. So the next step is to add the area layer. Each square here is one area, and we have about, well, 150 areas to highlight here the scalability of the approach. So in the next figure, you can see area 1, it's this one, and the foraging zone. These are all the red areas, red squares here in the graph of area 1. So the basic idea is if a vehicle is somewhere here and has a destination in area 1, the vehicle is routed toward the representative node of area 1 until the vehicle gets into the foraging zone where precise information is available. So let's come to some simulation studies. We've tested, well, in this simulation we have about 250,000 vehicles, and what you can see here is the travel time on this axis and several box plots. The first box plot belongs to the free flow time, and you can see that the next box plot, that's BeeJammer with a penetration rate of 100%, is really close to the free flow time. The next box plot is a dynamic shortest path algorithm with an update interval of 5 minutes. And you can see that there are a lot of outliers due to the traffic jam that arises in the network. So the next one is BeeJammer, but only with penetration rate of 30%. And in this example, you can see that BeeJammer with a penetration rate of 30% is, well, a little bit better than a dynamic shortest path algorithm with complete knowledge of the whole graph, which is quite an unrealistic scenario, so it's a quite good result. Well, in the next figure, you can see a clear tendency that, well, here is the travel time and here's the penetration rate, and I can see a clear tendency that as we increase the penetration rate of BeeJammer, the travel times decrease. So this is a simulation study of Shanghai. I've been in Shanghai last year and it was very overcrowded, so I applied the routing protocol also to Shanghai. So here we can see the same tendency. If you can see the green line, it's not very obvious. As we increase the penetration rate, the travel times decrease. Here the same with the box plots. Here's the free flow time. Here's BeeJammer 100% penetration rate, and here are the dynamic shortest path algorithms with varying penetration rates. So what you can see here once again is a figure of edgelords. This red, or each curve in this figure says, well, gives the number of edges with a specific edgelord. And what we can see here is that for the shortest path algorithms, the red curves, the edge load is steadily increasing, but not under pajama. It's more or less the same load all over the time. So let me conclude. I've presented a self-adaptive distributed vehicular traffic management system scalable to large regions, and our future work will be, well, multi-objective traffic flow optimization, for examples, and many, many more, and very important field studies. So I skipped some of the technical details, but you can find them in the paper. So that's it from me. So I'm open for your questions.
Okay, so questions? No questions?
Perfect.
No.
Perfect.
So, several curiosities. Real time. How is it required? To which extent?
So the question was real time. What's with the real time capability? Okay. Well, the basic idea is that the flooding process is more or less, well, a fire and forget approach. So, well, a lot of animations, sorry. So, this is the first step of one generation, and the transmission time of a B agent in a communication network is not very long, so it happens very fast. So the dissemination of local information is no problem. So there's not a real-time problem as such, but you're right, the dissemination must happen in due time so that the information when used to calculate detours is not outdated. Yeah, that's true. But we often update frequency of 1 second because disseminating of delays is not a big problem using a multi-agent system.
With my second question, 1 second update rate, is it required, is a must, or you can relax it? My feeling is that 1 second.
1 second, yes.
For updating the information, is it required, or is it minimum, is it whatever?
It's not absolutely required, but we can do it, so we do it. It's quite easy. Well, we want to show the difference to available systems. They offer static or centralized updates with an interval of 5, 10, or 15 minutes. And we want to show that it's possible to do it in a decentralized way much faster, to react very quickly, because more or less, if you do not rely on reservation mechanisms or something like this, it's a reactive system, and you must be quite fast to cope with the highly dynamic phenomena in traffic congestion. So if here is an accident, for example, and this edge is blocked, well, it's good for the user, for the driver, if the information is disseminated very quickly.
Okay, and oh, great. Another question, a comment. Okay, can you bring here the phone, please, or the microphone, please?
The comment is that the reason for that question as well, that we have the problem to give information, routing information, well before any intersection. And if you do not only work on freeways or on national roads or something like that, but have a very, very refined street structure, then it is a heavy real-time restriction. Speed dependent, of course, as you know, and still you have to, with 1 second you're on the safe side. That's why. If you can have a response, in case anything changes, of course, a response within 1 second, well, that you cannot simply be wrong as a driver. It will be there in time.
Okay. And any other question? Yeah. Please, the microphone over here, on your right, or on your left.
Yes, thank you. Can you give an impression about what would happen to a single car? For example, if you have this road network and then your B system might discover many empty streets and direct all cars go over there, you can drive without stopping, and then in your model you would notice no jams. Or do you really measure the travel times or the length of the roads?
Okay. Well, the most well-known system is some kind of floating car data, and that's commercially available today. But yesterday there were 2 workshops, one on IP version 6 and ITS, and one workshop on localization and navigation and so on. And this topic has been discussed heavily in these workshops, so it's a well-known research area. But for our application, simple floating car data stemming from GPS information, for example, is quite sufficient, because you just need an idea more or less how long it takes to drive through a given link or something like this. So that's not a big problem. However, you should not collect all the information centralized in a centralized fashion. That's a problem. The navigator, the local navigator, must do it in a distribute fashion, so that each vehicle, for example, and that the onboard units in the vehicle send the last link time to the local navigator, and then local navigator then has the area-related information and nothing more. So it's regionally limited information that you need.
Yeah, okay, thank you.
Any other question? Yes, over there, please. Oh, sorry, it's okay. You were later on.
Hi, Juan Aparicio from Siemens. So one question, are you assuming that for your model that all the cars need to send periodic information about their position, all the cars of the network, or just a few of them?
Well, the higher the penetration rate is, of course, the better it is, but these travel times over a link do not change, well, most of the time do not change rapidly from second to second. So if the 10th vehicle or whatever submits this information, it's sufficient. Okay. That's an answer to your question.
The last question.
Yeah, I have a question concerning the nature of your algorithm. I'm here.
Okay.
Okay. So there's something out there which also performs routing in a decentralized fashion. It's called the internet. And I wonder what the major difference between your kind of information collection and distribution is and the regular routing protocol of the internet.
To which routing protocol?
Internet, so IP protocol for routing in the internet.
Okay. Well, that's a good question. These distributed routing algorithm Beehive has its origin in a computer network routing algorithm termed Beehive. It was the first incarnation, if you want, from this multi-agent system. The problem is that classical IP routing algorithms like OSPF and something like this work in a very static way most of the time. You're right, they do not collect in a centralized fashion all the information. But it's not very dynamically. So as Beehive has been developed, there were a lot of comparison between OSPF and Dijkstra and whatever, and these multi-agent systems normally outperforms classical IP routing algorithms. But you're absolutely right, these algorithms have their roots in the routing in the internet.
Let's thank the speaker again. And we're moving to the last talk of today. Is there any author from, that I suppose is Howley going to present it? And the title is Cooperative Multi-Vehicle Localization Using Still Covariance Intersection Filter.
Good afternoon, everyone. My name is Howley. I'm from IMAHA team at INRIA France. Today, I'm glad to make a presentation on the topic Cooperative Multi-Vehicle Localization using Split Covariance Intersection Filter. The outline of the presentation is listed here. First, I would like to begin with the motivation and the research context. Vehicle localization is an important task for intelligent vehicle systems, and it has been intensively researched. But so far, most of the research work focuses on single vehicle localization. That means each vehicle performs localization based on its own sensor data. On the other hand, in traffic environment, there are many vehicles which might move and operate in the same environment. And besides, the vehicular communication technology has developed rapidly. So all this gives the vehicle a chance to interact or even cooperate with each other. Concerning about the purpose of localization, the motivation for developing cooperative localization can be well illustrated by this simple example. Here we have two vehicles, vehicle A and vehicle B. And each of them has self-localization ability, just like in single vehicle localization. They also have some vehicle sensing system based on, for example, laser scanner or other kind of range information sensor. So if we examine the localization aspect for vehicle B, first, it can be localized by itself based on its own data, as in single vehicle localization. Besides, it can also be indirectly localized from the perspective of vehicle A, as shown in the bottom subfigure. So if we fuse these two sources of data, we might get better localization results for vehicle B. The same can be applied to vehicle A too. Based on this motivation, we're researching into the topic of cooperative localization. First, we have to choose which architecture, which cooperation architecture we have to use. There are two commonly used architecture. One is centralized architecture, in which a fusion center gets the information from all the vehicles, do the fusion, and then sends the estimate to all the vehicles. Another kind is decentralized architecture or distributed architecture, in which in this architecture, each vehicle assumes the role of a fusion center. It gets the data from neighboring vehicles and performs fusion for itself. Centralized architecture is more convenient for processing data. However, it suffers from the problem of computational burden, communication burden, and delay. The most important is inflexible in dealing with the dynamic vehicle networks, which are common for traffic environment. On the other hand, decentralized architecture has low computational burden and for each fusion center. It's also flexible in dealing with the vehicle networks. So it's a desirable solution for cooperative localization in the long run, and we choose this architecture. And then concerning decentralized architecture, a fundamental and essential problem is how to handle interestimated correlation. Because naive handling of this correlation will result in circular reasoning, which will further lead to overconvergence problem. What further overconvergence problem means that the estimate of all the vehicles quickly converge to some inaccurate or even severely diverged estimates, where extremely large confidence are given to this estimate. A process of circular reasoning and overconvergence problem is illustrated here by three vehicles. Vehicle 1 gets a new measurement, and its estimate is refined by this new measurement. Then the refined estimate is passed to vehicle 2, which further refines the estimate of vehicle 2. And vehicle 2 passes this to vehicle 3, and again pass back to vehicle 1 again. After several rounds of this process, the estimate of all the vehicles will become overconfident and even more overconfident. So, since the overconvergence problem is due to interestimated correlation, a natural idea to deal with this problem is to monitor and control the data flow. Here are some examples. based on some rules of monitoring and controlling the data flow. Some rules are simple. For example, if the data of one vehicle is used to update the state of the other vehicle, and then the second vehicle, the estimate of the second vehicle cannot be passed back to the first vehicle during a certain period thereafter, as shown in the first two methods. And some method can be more complicated, as shown in the third method, and the implementation detail could be more complicated. However, the estimate can be comparable to some centralized estimate. However, the estimate is outputted with some delay, and the delay length is uncertain. Besides, large amount of data have to be communicated and related from vehicles to vehicles. And here is another typical example. In this method, a state exchange-based method, only independent information can be allowed to be shared within the vehicle networks. The merits of this method is that, first, it's simple and convenient to realize. Second, the risk of overconvergence is removed out. However, for this method, a vehicle can only benefit from the data of its direct neighboring vehicles. It cannot benefit from the data of some vehicles beyond its neighboring vehicles, which will be further demonstrated in experiment. And we can continue working in this direction on monitoring and controlling the data flow. We can continue designing some data transfer scheme to deal with the cooperative localization. But before we continue doing that, we can ask ourselves a question. Do we have to monitor and control the data flow to deal with the inter-estimate correlation? Actually, the reason that why in above method we need to monitor and control the data flow is because the fusion method used in above cooperative localization method cannot yield consistent estimates when the estimates are correlated to each other, especially when the correlation degree is unknown. So what if there is a fusion method which can yield consistent estimates even facing unknown degree of inter-estimate correlation? And the question is, what does consistent mean? Consistent means that the covariance of the estimate should not be smaller than the ground truth of the covariance of the ground truth. In other words, the estimate should not be overconfident than the truth. In fact, there is such kind of fusion method. Covariance intersection filter is such a kind of method which is theoretically proved to yield a consistent estimate even facing unknown degree of inter-estimate correlation. However, the original version of this method is a bit pessimistic because all the data in this filter are assumed to be totally dependent, and there is no independent information in the data to be fused. So later, an improvement on original covariance intersection filter was proposed. It called split covariance intersection filter, which allowed the no independent information to be considered and maintained in the estimate. The introduction of a split covariance intersection filter will naturally lead to the proposed method. The idea is to apply split covariance intersection filter for cooperative localization. And what's split covariance intersection filter? Here, imagine there are two estimates to be fused, x1 and x2. Each estimate can be split into two parts, which are indicated by the subscript D and I. D means dependent, I means independent. Imagine that x1D and x2D are correlated to each other, where x1I and x2I are completely independent. Then the fusion formula is shown here. This formula can also be represented in another way for like this for partial measurement model. If we can pay attention to this formula, if we set P1D and P2D to 0, that means if we assume there is no dependent information in the estimate, the formula will actually become the commonly used Kalman filter. So in some sense, we can regard split covariance intersection as some generalization for Kalman filter, and some generalization of a Kalman filter which can deal with the unknown degree of correlated data. And we applying this filter for cooperative localization, and before the further presentation, we will give some description about the configuration assumptions. First, we assume each vehicle has some absolute positioning function, for example, which is provided by global positioning system. We also assume that each vehicle has some relative positioning function, as I have mentioned, based on, for example, laser scanners. We also assume motion monitoring functionality for each vehicle, which can be realized by odometers and steering angle encoders. We also assume the communication function between vehicles, and each vehicle has a time stamping function, which relates the time of the data to the GPS universal time, so the data of all the vehicles can be referenced to the same time coordinates. And because the architecture is distributed, then we will present the cooperative localization method from the perspective of one vehicle. We call it echo vehicle. And this vehicle, it maintains the estimate, which is denoted by XE. For itself, it also maintains some estimate of other vehicles, which are represented by XO1 to XOM. And the localization procedures are just like we perform localization for Kalman filter. For example, we perform group state evolution, and we update the state of the state using some data. We have several kind of data. We update the estimate with the absolute positioning measurement using the formula here. We update the estimate of other vehicles using the formula here. We update the echo vehicle with the estimate of other vehicles using the formula here. Here, I just quickly go skip all these procedures without going into detailed explanation for each denotation. Actually, the basic idea is quite naive. If the vehicle has some data from its own sensor, it fuses it. If it gets some estimate from other vehicles, it also fuses it without caring at all at the data flow. The only difference with the naive implementation is that here we don't use a Kalman filter, we use a split covariance intersection filter. And then we'll go into the experimentation results. Here we do our test on simulation. The simulation scenario is a typical scenario of a long road where a chain of vehicles move on it. And there are 8 vehicles. Each vehicle can only interact with its neighboring. For example, vehicle 2, it can share data with the vehicle 1 and 3 because it can only perceive the data of it can only perceive vehicle 1 and vehicle 3, and it's similar for other vehicles. Since we do tests on simulation, so it's more meaningful than just demonstrating the performance of the proposed method. We made a comparative study. We choose several methods for comparison. One is single vehicle localization method, in which each vehicle performs the localization based on its own absolute positioning data, as well as the odometer method, as in a normal Kalman filter-based localization method. And the second method is called a naive cooperative localization method. Actually, for this method, each vehicle not only performs single vehicle localization, it also gets estimated from other vehicles. And when it gets estimates from other vehicles, it fuses this estimate with the Kalman filter or extended Kalman filter. And then the third is a state exchange-based cooperative localization method, which is given in this reference. And the fourth is the proposed cooperative localization method using split covariance intersection filter. Here is the result. First, we show the result in simulation configuration 1. In this configuration, all the vehicles, the absolute position measurement error are assumed same for each vehicle, and with the comparative large errors with a zero mean and a standard deviation of 7 meters. And the result is shown here. The black one, actually these 8 sub-figures on the top shows the result of the 8 vehicles. The horizontal axis means the time index, and the vertical coordinate means the positioning error, the Euclidean position error between the estimate and the ground truth. In each sub-figure, the black one means the result means the position localization error of a single vehicle localization. The green one means the position error of a naive cooperative localization. The blue one means the positional error of a state exchange-based cooperative localization method, and the red one is the result of the proposed method. As we can see, naive implementation of a cooperative localization always diverges the estimate largely, and it will go far and far away from the ground truth. And we can also see that cooperative localization result, denoted by the red one and the blue one, are always better than the black one. And maybe here it's not so clear. We compute the root mean square error of the whole localization process for all the vehicles, and we show the result in the sub figure. Actually, in the bottom figure shows 50 rounds of tests in this scenario, and the red one also, as in above pictures, the red one denotes the result of the proposed method. The blue one denotes a state exchange-based method, and the black one means a single vehicle localization error. And as we can see, cooperative localization results are always better than the black one. Maybe we think that the advantage of cooperative localization and the advantage of the proposed method is not so apparent. Then we'll move in a more exciting scenario. We also, like in simulation scenario 1, we also have 8 vehicles, and all these vehicles suffer from some absolute positioning measurement error of this distribution, except for vehicle 1. Only vehicle 1 has some relatively better localized absolute position measurement, which has an error of only 0 mean and a standard deviation of 0.1 meters. So what does this scenario mean? It means that in our road we have a group of vehicles, and only one vehicle has a comparatively good positioning configurations, and the positional errors of these 8 vehicles are shown here. And the first one is the localization result for vehicle 1, and vehicle 2, 3, 4, 5, 6, 7, 8. As we can see, for state exchange-based method, concerning vehicle 2, the localization error is largely reduced. However, since from vehicle 3 to vehicle 8, all these vehicles cannot benefit from the good data of vehicle 1, because in this method, only independent information are allowed to be transferred, so the good estimate cannot be passed on to other vehicles. And for the proposed method, the good estimate can be passed from vehicle 1 to vehicle 2 to vehicle 3 until vehicle 8, represented by the red lines. So what does this mean? It means that the proposal of cooperative localization method allows a vehicle the good data to be shared among a group of vehicles without being overconfident and without being overconverged to some states. So imagine that we have 10 vehicles. If one vehicle has the chance to get good data, then a good estimation for all the vehicles can be maintained. Then maybe at this time, vehicle 1 has good estimation. At that moment, vehicle 3 has good estimation. And maybe at that moment, vehicle 8 has good estimation. So by using cooperative localization, it's very likely that all the vehicles can maintain some good estimates all the time. Imagine that for each vehicle, it has only a probability of 40% of having good positioning measurement. For these 8 vehicles, for them, the possibility for them to have some good estimate will be almost 100%. You can do the calculation by yourself. Then I would like to follow my presentation by a conclusion. We have presented a cooperative localization method for multi-vehicles using split covariance intersection filter. And we have also demonstrated the advantage of the proposed method over several reference methods. In future works, since in this presentation work, we have done the test based on simulation. So naturally, field test will be the direction for our future works. And thank you all. Question?